All right, so welcome to MathStat 341. This is lecture 10, but it's going to be a slightly different lecture 10 because you were supposed to have watched lecture 10 for Friday's class, which became Mountain Day. So this gives us an opportunity to just talk about some interesting issues in a little greater detail. If you do have questions from that lecture, I will try to leave some time today for those. What are we going to be discussing today? So we'll be talking a little bit about independence, a little bit about inclusion, exclusion. We've already seen a little bit about inclusion, exclusion. We'll talk a little bit about derangements. So these are when you commute and nothing returns to where it started. So some general items is, depending on how much time there is, we'll talk a little bit about proofs by induction. So out of curiosity, how many people have seen proofs by induction? Okay, excellent. So most people have seen proofs by induction. It is not a prerequisite for this course. It is useful in terms of being able to rigorously prove a variety of things. One place where proofs by induction is supposed to be seen in the curriculum is when you're proving the fundamental theorem of calculus. So when you're proving the fundamental theorem of calculus, you have the area under the curve is the antiderivative at b minus the antiderivative at a. Well, how do you know that you did your proof correct? Well, hopefully, you understand the logic as you go step by step by step. But it's wonderful if you can actually check this with some functions where you know what the area under the curve is. Well, the simplest functions to check is the function that's constant, which gives you a rectangle, or the function, y equals, say, 3x or 5x or just constant x, but that's a triangle. So developing the fundamental theorem of calculus to find the areas of rectangles and triangles is really not that much of an achievement. So the first non-trivial one is to find the area under a parabola. And to find the area under a parabola, this can be done. And a great way to do that is induction. And this starts to show you, hey, we might have actually done something here. So one of the things is, we'll talk a little bit about that. We need to be careful sometimes in terms of what do we actually prove. It is very easy to miss that there are conditions going on and then just apply something without the conditions being seen, or as I have learned, people can ignore conditions you put in and quote things out of context. So you want to be extremely careful that when you do a proof, you understand what are the conditions, when can you use this. We'll talk a little bit again about definitions versus theorems. I talked about the fundamental theorem of calculus. If you just say the integral of f of x dx is big F of b minus big F of a, that's a definition. There's no content to it. The theorem is that the integral actually represents the area under the curve. All right, and so one thing that I do want to add in terms of general items, this is related to derangements, is study objects. So sometimes one object is easier to study than another. It's often easier to figure out the probability that something doesn't happen than to find the probability it does happen. So we've seen that already this year. What was something we saw, I think, even first day of the semester, where it was easier to calculate the probability that something did not happen than the probability that something did happen? Anybody remember? Birthday problem, right? Because if you want to calculate the probability that at least two people share a birthday, oh dear Lord, you could have 2 people, 3 people, 4 people. You could have a set of 4 and a set of 2. You could have 3 sets of 2. There's so many different ways of that happening. It's much easier to calculate what's the probability it doesn't happen, and then just subtract that from 1. Any baseball fans? There were a lot of very interesting calculations going on with 4 teams that could conceivably have made the wild card yesterday as to just what were the chances of different teams making it. All right, so I don't want to go into too much detail as this stuff was in the book and this was in the video we were supposed to read. I just want to go through a few quick highlights of some of the stuff. So we were talking about independence. This is one of the biggest items. A lot of times, events are clearly independent. So I am wearing my Lucky Red Sox shirt. I don't wear it that often. I only wear it in extreme situations when the Sox absolutely need to win. And it does a really good job. True or false? False, right? Can you prove that my wearing the shirt does not make a difference? No. There's a lot of strange, sports superstitions. One of my favorite commercials for one of the Bud, either Bud or Bud Light, is a woman in San Francisco goes into her living room and sees a strange person sitting on her couch. And she looks at him, what's going on here? She goes, this used to be my apartment, and whenever I sat here, the Niners always won their playoff games. And she looks at him and she goes, and you're only showing up now? So we have a lot of superstitions that we think, or just it makes it a little bit more fun to just play along. But
It doesn't work.
exactly. I've got to just say this, but yes. Absolutely, of course it works. Was that Pet Detective?
I don't remember from a Bud Light commercial, but
Okay, I was thinking the Jim Carrey movie Pet Detective, Ace Ventura Pet Detective, but it's been used many places. So a lot of these things, they're clearly independent. The shirt I wear and how the Red Sox do in games, these should be independent. Other things are a little bit harder. So if you're spinning the wheel and the price is right, and you're trying to get two spins that sum to as close to $1. Well, when the first spin ends, you're spinning from that point, not from the initial point. So there is some dependencies between the spins. So you really want to think, do I have events that are independent or not? So the informal definition of independence should be knowing one event happens gives you no information about the other event. So the probability of A given B should be the same as the probability of A. The probability of B given A should be the same as the probability of B. But what happens is we have more and more events. So let's let A, B, and C be the following events. A is the event that the first die is an even number. B is the second time the die shows an even number, and C is the sum of the first two numbers is even. So we're rolling a die. A is the first time we have an even number. B is the second time an even number, and C is the sum of the two numbers is even. And if you go through the different probabilities, you can show that the probability of any two happening is the product of the probabilities. So any two of the three events are independent. But clearly, the probability of all of them happening is not the product of the probabilities. Because if you know A and B happen, if the first roll is even and the second roll is even, then the third roll has to be even. So for independence, it's not enough to check just pairwise. You have to check all possibilities. And so, the formal statement, I guess I didn't bother writing it formally, but so the formal statement is just any subset. When you take them, the probability has to be the product of the probabilities. It's not enough to just do pairs. If I have 4 events, it's not enough to do pairs and triples. Okay. Next one that I want to just briefly talk about was Bayes' rule. And so this is used a lot in some of the advanced statistics classes here. Strongly urge you to take those. So the general multiplication rule states the following. The probability that B happens given A times the probability of A is equal to the probability that A happens given B times the probability of B. And the point of this is it allows you to pass from knowing the probability of one event given another to them in the opposite order. And so why is this true? So can somebody remind me, what's the connection between the probability of A given B and the probability of A intersect B? So how are they related? Good. So the probability A intersects B over the probability of B, or the probability of A intersects B is the probability of A given B times the probability of B. And then if you just switch the roles of A and B, by symmetry, this is the same as the probability of B given A times the probability of A. If you want, this is just the probability of B intersect A. So it's always nice when you can just use the symmetry argument and avoid a lot of calculations. This is similar to when we were doing the combinatorics and the sneetches with stars on their bellies. If you choose K out of N to be starred, that's the same as choosing N minus K out of N to be excluded. So I can view the probability of A intersect B as the same as the probability of B intersect A. And so when you look at it this way, now all of a sudden, Bayes' rule is quite clear as to why we have something like this. And so what we can do is we can isolate and we can find the probability that A happens given B is the probability that B happens given A times the probability of A over the probability of B. So just because we have a formula like this doesn't mean it's useful. I can write down a lot of useless formulas. I'm a professional mathematician. Why is this useful? Because sometimes certain events are easier to compute than others. And the goal is, whenever possible, convert whatever you are given to something that you can do. Think of it as a presidential candidate being asked a question in a debate. Doesn't matter what you're asked, you convert it to something you want to talk about. If I can compute certain probabilities, then if you want something else, how can I write what you want in terms of what I can do easily? And that's where Bayes' rule is extremely useful. So here is one of the most common examples. This is from the textbook. This is from a couple of years ago. Give me a question. Instead of using tuberculosis, what would we use today? COVID. Yeah, exactly. Right. So this is extremely valuable. So nationwide, tuberculosis affects about 1 out of every 15,000 people. Suppose you get a TB. There's a TB scare in your community. People think that it's running rampant. And let's assume that you go to the doctor to get tested. The doctor says it has a 1% false positive rate. So that means out of every 100 people who are healthy, 1 out of 100 people will test positive, even though they don't have it. Okay. So I told you about the false positive rate. What else might you want to know? The false negative rate. And so the doctor reveals the test has a 0.1% false negative rate. So that means of every 1,000 sick people, only 1 will test image. Only 1 will test negative. Is that the right way to phrase this? Okay. So suppose you test positive. So you are just told you have a positive test for tuberculosis. Or if you want, you can update it to COVID or whatever deadly disease you want. How scared are you? You've got a positive test. Not very scared. Why? Right, so the incidence is very low. It's 1 out of every 15,000 people. And because of the way these numbers are, it's actually more likely that you have an incorrect test. So what happens? What should you then do? Well, you base them, of course. I mean, when in doubt, use math and stats. But what should you do if you get a positive test? Take another one, right? So what you often have is you often have a cheap test, and you might have a better test that is less likely to make an error. Hopefully the tests are somewhat independent. So if there's a reason why you tested positive, you won't, other than of course you have it, you won't test positive again with something else. So Bayes' theorem tells us the probability that you're sick and that you're sick, given that you test positive, is the same as the probability of being sick divided by the probability that you're positive, times the probability that you're positive, that you test positive, given that you're sick. So the question is, which things are easier to compute? So is it easy to calculate the probability that you're sick? Yeah. What is this? This is 1 in 15,000. Easy to find. Okay. What about the probability that you're positive given that you're sick? Here are the false negative, right? So we can do this. What about the probability that you're positive?
Yeah.
So there's several different ways you could test positive, but this seems okay. And so let's just go through things very slowly. So we'll use the partition sick and not sick. There's 2 possibilities. You're either sick or you're not sick. And so what we're doing is we're splitting our event space into 2 disjoint things. You're not going to be both sick and not sick. So B is the event that we're sick. B complement is the event that we are healthy. Not sick. And so A is the event that we're testing positive. So if you want, we have a space omega, and we split it into sick, which is B, and not sick, which is B complement. And then here is the event A. Over here. So we want to figure out what is the probability of being sick, given that you have a positive result. So if you have a positive result, which side are we going to be on? We're going to be in the, so if we're sick, we're in B. If we're not sick, we're in B complement. Might have misspoke. Right. So let's find the probability that we're positive. So we have to split it into the different cases. How could you be positive? You could be positive because you are sick and you tested positive, or you could be healthy and you tested positive. So the way we find certain events is we break them up into disjoint possibilities and we calculate each one. This is like something else we did on the first day. Maybe it was the second day. It was a sports problem. Yeah, the Magic Johnson, Larry Bird. As a Celtic fan, I would have Bird first, please. So, what's the probability Bird wins? Bird could win on his first shot, Bird could win on his second shot, Bird could win on his third shot. We have a bunch of distinct possibilities. They're mutually exclusive, and they're exhaustive. They cover all possibilities. So if we can just figure out the probability of each one, we then sum them together. So how can I test positive? I could either be sick and test positive, or I could be healthy and I test positive. And I just calculate each one. So what is the probability that I am sick? So that is 1 in 15,000. And then the probability that I test positive, given that I'm sick, is 0.999. It's really, really likely. And then what's the probability that I test positive if I'm healthy? That was the 1%. And I have the probability that I am healthy, which is 14,999 over 15,000. So what you see is this fraction is so close to 1, and this fraction over here, 1 over 15,000, is so close to 0, that even though 0.01 is much smaller than 0.99, this is so much closer to 1, and this is so much closer to 0, that the resulting expression is approximately 0.01. Is that there's so few people who are sick. So we get the probability that you are sick, given that you're positive, when you put everything in, is just 0.0066. Now, if you multiply by 100, that's 0.6%. This is not a significant number. So I like doing this with the expected counts approach. So we start off with 15 million total people. Why 15 million? Because 1 out of every 15,000 is sick. And this just gives me nice numbers as I go through. It's nice not to be talking about a third of a person. And so if I have 15 million total people, 1,000 are infected, and 14,999,000 are not infected. So it's very rare to have somebody infected. So this is not the same as COVID. These numbers are very different. And so now if you look at the infected, there'll be 1 negative test and 999 positive tests. And if you look at the people who are not infected, who are healthy, there'll be 14,849,010 negative tests and 149,990 positive tests. So you see that most of the positive tests in this case are coming from the people who are healthy. And this has tremendous implications in medicine in terms of what do you do. The most important thing is, you want to make sure that somebody who might have it is tested, gets the treatment they need, doesn't infect other people. But at the same time, you don't necessarily want to worry everybody. So I know this is being recorded, so I will phrase this as hypothetically. What might you do if somebody tests positive to a deadly disease, and let's say there's no cure? When is quarantine? How do you break the news to them?
Walk in and say, hey, that's the cause of this disease.
Are your wills in order? Have you
That, it's like this, we probably test them again too, if possible.
So do you lead with you've just tested positive for a deadly disease?
Yeah, I totally leave it like you did this positive, but
So this becomes an interesting situation. Do you say you tested positive, or do you say the test was inconclusive? Yes.
Well, I'd probably go with telling he's positive, because otherwise he might go off in the community and say, oh, there's.
So
a small chance,
so
like,
you need to make sure they get tested again, especially if it's something that's contagious. But you want to be very careful as to what kind of emotional state do you put people through. You know, if most of the people are going to actually be healthy, do you want them to all of a sudden be thinking they're about to die? You could, of course, lead with a brief lecture on Bayes' theorem. Good luck with that, with the general population. But it's an interesting thing to think about. How do you want to break the news? Different hospitals are much better at dealing with patients than others. There are some children's hospitals which are absolutely outstanding in terms of how they keep people relaxed in terms of what's going on. But this is just something that you really want to think about as to how do you report these results, which, at this point, just because you have a positive test, there is a significant chance that the test is wrong. For a lot of things, you want to make sure people stay on medicine. So even if it's no longer needed, there could be such a harm of them getting off. You want to make sure that they keep taking it. And so we can definitely talk about stuff like that. Okay, so we've been using the following result many times. Let's just extract it right now. It's the law of total probability. So say we have a set of events that form a partition. So what they mean is it's disjoint, and their union is the entire outcome space. So again, always think of a concrete example. For me, it's the bird playing magic. Does bird win on the first shot, second shot, third shot, etc. These will partition the game into disjoint, exhaustive options. So the probability that A happens is just going to be the probability that A happens given that Bn happens times the probability that Bn happens. And so this is a very reasonable thing. I just keep splitting my space into different slivers. And I look at how often does Bn happen? And then if Bn happens, what's the chance that A happens? And I add them all up, and that will give me the total probability of A happening. Now, we should technically have, maybe the probability of Bn is, greater than 0. Because when we talk about the conditional probability, we do talk about how, the probability of Bn should be positive. Otherwise, what does it mean to say, what's the probability A happens given B happens and B can't happen? But if you look at a formula like this, I'm then multiplying it by the probability of Bn. And if the probability of Bn is 0, I'm multiplying it by 0. So if you're willing to just accept that it doesn't really matter what the probability of A is given Bn if Bn doesn't happen, because it's got to be something between 0 and 1, I hit it by 0, I can include that in my space. So for instance, I could include in my partition the probability that bird wins on his negative third shot. Right? So usually the Bn's will always happen, but if you have a few that happen with no probability, it's not a big deal. And then here's another way of just rewriting Bayes' theorem. The probability A happens given B is the probability B happens given A times the probability of A divided by the sum of the probability of B given AI times the probability of AI. What is the sum on the bottom going to be? So what is the denominator? It's just the probability of B. So this is just a nice way of writing Bayes' theorem. And in fact, we actually computed things like that. We calculated what's the probability you have a positive test by splitting things into sick and healthy. And again, all of this comes down to trying to figure out what is the best way to compute things. And again, I've told you, I think that the exam, I've told you what type of open book exam it is, what you're allowed to use. So I am not expecting you to have all the formulas and everything memorized. And you can click on anything on the web page, but you can't click more than just one link off of the web page. Okay. So another thing that's just worth mentioning is the at least to exactly one method. We've actually seen this already in the semester. And this is one of the advantages of doing some of the applications. When we did the German tank problem, we wanted to calculate what was the probability the largest tank observed had a serial number of m. Well, we looked at what is the probability that the largest serial number observed was at most m. We looked at what was the probability that the largest observed was at most m minus 1. And their difference will then be the probability that the largest observed was exactly m. This is just doing this in the other way. If you want to know what is the probability for at least k things to happen, if we know that, we can go from that to knowing the number of ways to have exactly k things happen. So to have exactly k things happen, you have at least k things happen, and you subtract off the probability that at least k plus 1 things happen. And this just tells us that if we can compute at least, we can then trivially get exactly. Do you think you can go in the other direction? If you can compute exactly, can you get at least? As long as this is countably many. If you want to calculate what's the probability that at least 5 things happen, it would just be the probability that exactly 5 happen plus exactly 6 happen plus exactly 7 happen. So we can go back and forth between the two. It's just a question of which calculation is easier. All right, then the big part of the lecture was counting derangements. So when you have n objects and you reorder them, what is the probability that nothing returns to where it started? And so we go through that and use a lot of inclusion exclusion on that. I thought I would talk a little bit in detail about that because that's a nice example of inclusion exclusion. So derangements. So order n objects, nothing returns to start. So if I gave you 1, 2, 3, 4, 5, and I wrote 5, 3, 2, 1, 4, where I gave you 1, 2, 3, 4, 5, 2, 3, 1, 4, 5, this would be a derangement. And this would not be, because here, the 4s and the 5s return to the same spot, but in the first one, nothing returns. So the question is, why do we care about derangements? And then how do we calculate the probability something happens? This can actually be used in network theory. So let's say you're trying to build a system and you want various places to be able to communicate. There was a nice issue, I think, over the summer where world shipping was disrupted for an unbelievably large number of days because of a whoopsie. Anybody remember this? Okay, what was this? Yeah, the ship in the Suez Canal. And so you had a transit point where you can connect from the Mediterranean to the Indian Ocean very easily if you can go through the Suez. And if you can't, all of a sudden now you're going to go all the way around Africa, and that adds a tremendous amount of time to shipping. So when you have a network, you want the network to be well connected. The better connected the network is, the more you can just quickly reroute. Where is the other place in the world where if things go wrong, it's going to be real bad? Panama Canal. You lose the Panama Canal, oh dear Lord. You have two options. You go all the way around South America. We're not doing the Northwest Passage. Or you now have to stop on the Pacific Ocean, ship overland, and put it on ships on the other side. So you want to have a network where if you lose a few points, you can reroute without too much trouble. What is essentially a way to build a network so that any place can communicate with any other place very quickly? Can somebody give me a network? So you have a bunch of vertices and you want to put in connections so that everyone can communicate with everyone very quickly. How could we do this? Yes, if we just have everyone connected, does everyone agree that this will satisfy the requirement? So why don't we just do that? I'm sorry? It's expensive, right? So this is the complete graph, but it's expensive. If you have n vertices, have how many edges? So we have n vertices, how many edges would we have? Well, every vertex is connected to every other.
I mean, that's n plus 1 times 10.
Almost. Not in factorial,
N minus 1 times n minus 2.
not quite.
Yeah.
So there's a couple ways to look at it. Each vertex is connected to how many things? So each vertex is connected to n minus 1, and we have n vertices, right? So we have n minus 1 times n edges. But how often is each edge counted? I'm sorry? Twice. So we divide by 2. So that's one way to count how many edges we have. Each vertex is connected to n minus 1 objects. And we have n of them, so it's n times n minus 1. There's another way to view this. It's just n choose 2. How many ways can I choose 2 objects from n to connect? So this is basically approximately n squared over 2. So this is expensive. So you can do it a lot better by using deregular graphs. And so each vertex has exactly d neighbors. So if each vertex has exactly d neighbors, then how many edges would we have? So we have n vertices times d, right?
Oh, yeah.
Divided by 2. So this is of size linear in D, I'm sorry, linear in N. And so as long as D is fixed, it's going to be linear in N versus quadratic in N. So the question is, can you construct a graph that has good connective properties? And you can imagine that this is extremely valuable because it's expensive to put in cables. It's expensive to have networks. So, now that things are wireless, it's not quite as bad. But for instance, for the military, you may need to have very secure landlines where you don't want to risk not being able to send a message. It turns out that for many things, random graphs work. And I've done a lot of research with students on stuff like this. And so one thing you do is you take the numbers 1, 2, 3, ... n, and then you permute the order. So maybe it's 4, n minus 6, n minus 8, and 7. And that starts giving you connections. What's the danger when you're connecting something like this? Right. What's the danger? Because I want to connect vertices to vertices. So what's the danger in the permutation? What don't I want to happen? Yeah, we want to avoid connecting a vertex with itself. So need to avoid a vertex connected to itself. So it turns out counting the probability of a derangement is actually very helpful in trying to figure out if you just choose graphs randomly and make connections like this, what's the probability you're not going to connect things to themselves? And so this leads to a way to construct some graphs which can do a lot of great things. So you want to find the probability of a derangement with n objects. So we have the numbers 1 through n and nothing is connected to itself. So instead, it might be easier to calculate the probability that something is connected to itself and subtract. So this is just 1 minus the probability something connected to itself. And now we could have really good events. So A1, well, actually AI is the event I is connected to itself. What would AIJ be? Not I connected to J. Is I to I and J to J, and I does not equal J. Because if I equals J, I want to assume it's distinct. And in the Shaka, IJK is the event I goes to I, J goes to J, K goes to K, all distinct. So what's nice is all of these events have the same probability. All the AIs have the same probability. All the AIJs have the same probability. All the AIJKs have the same probability. How many of these are there? How many events AI are there? I'm sorry? N, right? How many of these are there? And choose two. I have to choose two indices I and J that are not the same. For the next one, how many? And choose 3. So we have the number, and then we have the probability. So what is the probability that I is connected to I? 1 over n. I has a 1 over n chance of being connected to itself. Another way of writing it is it's n minus 1 factorial over n factorial. Why do I want to write it like that? I have to connect I to itself, and then I have n minus 1 factorial ways to connect everything else. And there's n factorial total. So what's the probability of AIJ? So the denominator should still be an n factorial. And then for the numerator, I goes to I, J goes to J. That's forced on me. And now I have n minus 2 objects that I can put anywhere I want. So it's just going to be n minus 2 factorial. And then for the next one, I again have n factorial ways of connecting things. I, J, K have to go to specific spots. So I'm then left with n minus 3 factorial. And so the point is, these events are actually pretty easy to compute. And now, if I want to calculate the probability of a derangement, oh dear God. Yeah, so that means no object is connected to itself. So I start connecting, 1 to something and 2 to something and 3 to something, and then at the very end, maybe I'm forced to connect 7 to 7. It's much easier to do inclusion exclusion. So if I give you I1 to IL, we have this n choose L times with probability n minus L factorial over n factorial. So their product is going to be n choose L, n minus L factorial over n factorial, which is just n factorial over L factorial, n minus L factorial, n minus L factorial over n factorial. This is known as life is good, right? The n factorials cancel, the n minus L's cancel. And this is just equal to 1 over L factorial. So what is this? This is the probability, this is the number or the probability that I have these L objects going back to where they started. And I go over all the possible ways that this could happen, all the possible choices of L objects to go to themselves. So the probability that a specific set of L objects is just the n minus L factorial over n factorial, and the number of ways I can have this happen is n choose L. And so now the probability of A1 union AN, this is the probability that something returns to where it started. So something returns. Is just going to be a sum. L goes from 0 to n. There'll be -1 to the L, 1 over L factorial. I'm sorry? What do I start at 0? Do I want to start at 1? Yeah, so I think, yeah, so yeah, so I want to start at 1. Thank you. So it'll be L goes from 1, and this will be L plus 1, because we start off with a plus 1. So this is really coming from, the sum, I goes from 1 to n of the probability of AI minus the sum I less than j less than equal to n greater than equal to 1 of the probability of AI intersect AJ plus dot dot dot. And this event here is just the event AIJ. So this is the inclusion exclusion formula that we have, right? And so what happens is we do the analysis. So we get the probability of A1 union AN is the sum L goes from 0 to n, -1 to the L plus 1, 1 over L factorial. And this is equal to 1 minus the probability of a derangement. So that means the probability of a derangement is just going to be 1 minus the sum L goes from 0 to n, -1 to the L plus 1, 1 over L factorial. But because I have that -1, I have a -1 to the L plus 1. If I pull out a -1, they reinforce. So I hope I haven't done wrong. So I get, oh, sorry, the sum is L goes from 1, sorry. So we just get 1 plus the sum L goes from 1 to n of -1 to the L, 1 over L factorial. But how can you write 1? But 1 equals, I want to make this, I have a sum going L goes from 1 to n. So -1 to the 0, 1 over 0 factorial. So this is now the sum, L goes from 0 to n of -1 to the L over L factorial. But e to the x is the sum n goes from 0 to infinity of x to the n over n factorial. So e to the -1 is the sum n goes from 0 to infinity of -1. Well, instead of using n, we just use L so it matches. Is L goes from 0 to infinity of -1 to the L over L factorial. So it converges to 1 over e. And it's amazing how many problems in probability have as their answer 1 over e. It turns out this comes up many, many times. But we were able to calculate the probability of a derangement without too much trouble. Now, L factorial is growing extremely rapidly. So as n gets very, very large, the approximation of this to 1 over e is really, really good. It's also alternating so that, as you keep going further, they're going to be alternates. In terms of bounding it, you can even bound, am I too much or too little by how much? So the probability that you have a derangement is about 1 over e. Is that a sizable probability? Yeah. So there's a significant probability that nothing returns to where you stop. If you do 2 back to back, is it likely that both of them are derangements to the original? Yeah, that would be like 1 over e squared. That's still sizable. The more interesting question becomes, if you do all of them together, what's the probability that 2 of them have something that's the same? Comparing both of them to the first. And so you can try to ask questions like that. Right. Any questions on anything we've done up till now today or stuff from the meeting? So I'll then end, we've got like 4 minutes with induction. So you have a statement Pn, and you show P0 is true, and you show if Pn is true, then Pn plus 1 is true. If do this, Pn holds for all n. And the proof is actually pretty nice. So we know P0 is true. And if we take n equals 0, that gives us P0 true implies P1 is true. So what can we now deduce? So we know P0 is true. And we know that if P0 is true, then P1 is true. So therefore, so we know P1 is true. Now we take n equals 1, and it gives us P1 true implies P2 is true. So what can we now deduce? P2 is true. And you just keep marching down. So the standard example is, let's say, Pn is the statement that 1 plus 2 plus, well, we'll do 0, plus n equals n plus 1 over 2. So the base case, look at P0, is 0 equal to 0 times 0 plus 1 over 2? Yes. So inductive step. So assume Pn is true. So we know 0 plus n is equal to n plus 1 over 2. We must show 0 plus n plus 1 equals n plus 1 plus 1 over 2. But if you look at the beginning, by the inductive assumption, what do we know about 0 plus dot 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 plus n? By induction, it equals n times n plus 1 over 2 by the inductive assumption. And so if we then add n plus 1, we'll write it as n plus 1 times 2 over 2, it gives us n plus 1 times n plus 2 over 2. And that proves by induction that the sum of the first n integers. So if there is time, in the next class, I will prove everybody in the world has the same name by induction. I need at least one student to bring a valid ID to that lecture. Otherwise, we'll prove everybody's names to you. All right. Have a great rest of the day.